Lesson 2.6, Perimeters and Areas of Similar Figures. Your goal is to understand the things we discussed in class in regards to the connection between perimeter and area, specifically in relationship to similar figures. All right, so let's take a look at some of the examples that are similar to the ones we did in class. So in one of the problems you investigated, we looked at two similar squares, in this case a 3-foot square and a 6-foot square. And we discussed how you could view those two corresponding sides as a ratio. In this case, 6 feet to 3 feet, which would reduce down to 2/1. So there's a 2-to-1 correspondence, meaning this side of the square is twice as big as this side. And there was a direct connection between that and perimeter. Perimeter, of course, is finding the distance around an object. So in this case, a 3-foot square, we're talking 4 different sides, 3 feet each, and then 6 feet on each side for this square, which would give us perimeters of, for the small square, 12 feet, and for the large square, 24 feet. And it turned out that if we took these numbers, the perimeters, 24 and 12, and we put them into a similar ratio, and then reduced it, that it always turned out that the ratio of corresponding sides was the exact same ratio of perimeters. And so we get this, that when two figures are similar, the ratio of their perimeters is equal to the ratio of their corresponding sides. All right, so that helps us out in a lot of situations where we have really limited information, like this example here. Here I've got two trapezoids. This side of the small trapezoid is labeled 2 inches. Its corresponding side is 5 inches. And we are going on the basis that these are similar shapes. Now, the only other thing they've given us here is that the whole perimeter around this trapezoid is 12 inches, but we don't know the perimeter of this one. But even though all we were given is the 2-inch and the 5-inch side, this is enough information. So what we do is similar to what we did in the last slide. We first look at the corresponding sides, 5 inches to 2 inches. And then what we do is we do the same thing with the perimeters, that our unknown perimeter, we'll call it P for our variable, corresponds to the perimeter of 12 inches, so P to 12. If we cross multiply, we get 2P equals 60, divide both sides by 2, we get P equals 30. So the perimeter of this trapezoid is 30 inches, based on the fact that we're looking at similar shapes. All right, now let's move along. Let's go back to our example, but let's move on to area. Now area, it's a little different because area we're measuring something in 2 dimensions. Perimeter is a 1-dimensional measurement, meaning we're measuring a length. Anything you can measure with a ruler is a 1-dimensional measurement. But with area, we're measuring 2 dimensions. We're measuring the inside. How many square feet fit inside this shape? All right, but the nice thing is we start off the same. We first do a ratio of corresponding sides, 6 to 3, which once again, of course, reduces down to 2/1. Now, of course, with area, we don't need all 4 sides because area of a square is length times width. So we just need to know that this is a 3x3 square, and that would give us 9 square feet. Same thing with this one. This is a 6x6 square. 6 times 6 is 36, so we get 36 square feet. Now what we do is we take a look at that ratio, 36 square feet to 9 square feet. And if we reduce it down, we get 4:1, which is not the same as 2:1. Well, like we did in class though, we did different squares and different shapes, and eventually we came to the conclusion that if you take the ratio of corresponding sides and square those numbers, you get the ratio of areas. So in other words here, 2/1 squared equals 4/1. All right, so what that tells us is this, that when two figures are similar, the ratio of their areas is equal to the ratio of their corresponding sides squared. So I find the ratio of corresponding sides, I square those numbers, and that'll give me the ratio that is shared between their areas. So for a problem like this one, it's really useful. I've got two similar parallelograms. The bottom of this parallelogram measures 5 centimeters. The bottom of the larger one measures 15 centimeters. The area inside this parallelogram is 10 centimeters squared, and we don't know the area of the large one. But once again, with this limited information, that's enough. So what we can do is just like before, we first look at the corresponding sides, 15 to 5. 15 over 5 reduces to 3 over 1. So the ratio of corresponding sides is 3 to 1. Now, according to this definition, if I take that ratio and square it, that'll be the ratio between their areas. So if I take 3 over 1 and square it, I get 9 over 1, meaning that the area in this parallelogram is 9 times bigger than this one. And in fact, since I've got it here, let me show you how that actually works. If I actually take 9 of these, and of course it's not going to fit perfect because I had to draw out these parallelograms, but it's going to be close, that it's basically saying I can fit 9 of these inside the larger parallelogram. And so that's a nice visual seeing the 9 to 1 ratio, not 3 to 1. Okay, so now what I can do is I can say, well, I now have the ratio between the areas, which is 9 to 1, and this is our area. Let's call it A for area. So there we go. So the 9 to 1 ratio between their areas is the same as the missing area, A, over 10. So 9 over 1 is equal to A over 10, and if we solve that, we get cross multiply. 1 times A is 1A, 9 times 10 is 90, get rid of the 1. So the area of this one is 90 centimeters squared. We should probably label this centimeters squared. All right, so it's very similar to finding perimeter, except we're looking at the ratio of corresponding sides squared as opposed to just the ratio of corresponding sides, period. All right, so that's hopefully what we picked up in class, and this is what you're going to use to finish off your work.